Hello everyone, thank you for joining this session. My name is Mengna Ding, I'm your presenter today. During this webinar, we'll showcase the functionalities and advantages of ETAP eTrax, a streamlined solution tailored for enhancing real power systems, with a particular focus on analysis and optimization. During this webinar, we'll commence by providing an overview of the solution, why you need a tool for railway systems modeling and analysis, and why ETAP is the right option. Following that, we'll illustrate how to utilize this product to model, simulate, and analyze railway power systems, emphasizing its seamless workflow and superior efficiency. Additionally, we'll briefly introduce how the product integrates with other products in ETAP and real-time traction power management systems. Without further ado, let's start. ETAP eTrax is the software solution for design, analysis, optimization, and operation of integrated AC and DC railway traction power systems. It is broadly used by consulting companies, design institutes, rolling stock manufacturers, project developers, owners, and operators. Now, let's get clear with why is eTrax needed. During the initial design phase and before commencing constructions of a new transit system, eTrax can help to determine preliminary locations for substations and confirm the feasibility of proposed system characteristics. Some examples are the overhead contact system conductor sizes, the nominal and minimum system voltages, and substation ratings. And then at the design progress, modeling and analysis using eTrax becomes valuable for confirming and finalizing systems and equipment characteristics, as well as developing the engineering estimates of relevant system performance metrics. For example, the energy assumptions and vehicle runtimes. When evaluating existing systems in response to changes in operation levels or the deployment of new vehicles with updated performance characteristics, you can use the solution to identify areas of the traction power systems that may require capacity updates. Modeling and analysis can be conducted at any stage to assess new or previously unforeseen changes in operational levels, outages, or reconfigurations of the wayside traction power distribution systems. Okay. Now we know why you need such a tool. Let's see what makes eTrax stand out among the tools. eTrax serves as a one-stop solution, which contains all the information you need regarding the geospatial, landscape, routes, rolling stocks, train timetables, and your wayside electrical systems feeding the trains in one centralized database. We use this information to analyze and improve train performance and manage the systems. With eTrax, all this is done with an easy-to-use graphical user interface, which we will soon demonstrate. And also, this can be expanded to a traction eSCADA with real-time predictive simulations. With such a comprehensive solution, you can go from design to operate. Next, we'll showcase some of the cool features so you get an understanding of how the modeling, simulation, and analysis can be done efficiently using this tool. Let's start with modeling the geospatial conditions of your railway systems. Considering the complexity of railway networks, most users choose our data exchange functions to import the track layout. For existing railways, OpenStreetMap and LandXML are the most popular formats for railway data import. If you are designing a brand new system, then the existing database won't be available. ETAP provides the option to import through Excel, where you can define the passenger stations, platforms, track segments, speed limits, elevation curves, and so on in an Excel. You can also set the bounding and grounding points. ETAP will generate a preliminary model for you. Now, let's use the program to show you with an example of OpenStreetMap import. I just created a brand new ETAP project. Now I'm going to the geospatial view. And under Data Exchange, I'm able to select the import OpenStreetMap file. I choose to import the project as in DC. It will just take a couple minutes to get all this procedure done. So I select OK to use the default mapping tool defined by ETAP. Now the process XML file is done. Let's just see how it looks like after we import the map. So you can see that the passenger stations and the tracks are now imported into ETAP. They will automatically be laid on top of a Google Map that we selected as the map tail for this project. Now let me turn off the Google Map so that you are able to see it more clearly. The blue shapes imported are the train stations, and the gray color lines are basically the tracks imported just from the OpenStreetMap file. So the next step you are going to do is to define the track groups and the train routes. Let's see what I'm going to do. So I'll zoom in one train substation, highlight a track segment. You will notice that at this moment, on the right toolbar, you get access to all the AC traction elements, DC traction elements, and the train markers. So I'll go over them while I add more elements to my system. So the moment you highlight a track segment, the DC platform will be available for you to choose and drop inside your train stations. Let me just drop another couple more platforms. I'll do it for the adjacent 3 substations, 3 train stations. Other than the platforms, you have also the other options to drop the insulators with isolators and of different types of switches. Under the traction markers, you have the different options such as the train speed limit, the distance marker, the elevation marker, and the bend radius to define the curves, and also the coasting limit markers. So now let me just add a few of the markers to my system. I can add some curves to my system and maybe an elevation marker too. So the next step for us to do is to create track groups. That means you define the components from one platform to the next platform to complete from one station to another. What I'm opening right now is the eTracks editor. We're going to go over all the pages. So first, I'll define a track group, and then I can pick the components to form my track groups. When there are multiple paths, you will be prompted to select which direction to go. You see now I did my first track group by defining from the first platform the track, the markers on top of it, and then finish with the next track group. So now let me quickly add the second track group. This is how I can define my two track groups. Now let's define a route. The route basically means you can pick multiple track groups and to form your train routes, for example, from train station 1 to train station 2. What I'm going to do is that I'll select my track route 1, click on Update Elements, and just click on the first platform. It will automatically pick up all the following track groups starting from this platform as what you can see in the ETAP diagram. One highlight of ETAP is that it is able to automatically synchronize the geographical interface with the one-line diagram. So when I click on this button, it automatically generates a corresponding one-line electrical scheme. Now let's align the train stations to a way that looks similar to your electrical one-line diagrams. I'll select one train station and align it. You can select the space between the train stations when you do the alignment. I'll just go by medium, and then I choose to hide the elements that's not part of the train routes. Now you will see that the components I just created and included in the train routes are now becoming part of the components on my one-line diagram. My next step is to add the wayside electrical contribution systems. ETAP supports different traction power system types, like AC and DC. You can model the systems with auto transformers, booster transformers, Schottky transformers, and rectifiers. Also, same as the other modules in ETAP, we support any voltage level. You can also model the wayside energy storage systems on your one-line diagram. And all the single-line diagrams, you can use the templates to create the overhead conductor systems, the train substations, and so on. Let me show you how it looks in ETAP. If you are familiar with the ETAP template feature, you will know that ETAP by default provides you different configurations like substations that you can choose from and directly drop onto your one-line diagram. You can also create your own templates if many of the substations in your system follow the same pattern. The templates can be added onto your one-line diagram by just select it and say apply or OK. After that, you can do the connection from your substations or electrical power feeding systems to your traction systems. Based on your needs, you can create various applications and templates for the future usage to be more efficient, to save your time and proceed with your work efficiently. This is one example file I have put together ahead of time. So I'd like to show you the functionalities within this completed project. First of all, you can see that the train stations and the routes are defined and the routes are colored differently to indicate the location. Let's take a look at the eTracks editor again. There can be multiple track groups defined with all the components inside, including the platforms, track nodes, speed limits, elevations, curvatures, and so on. With all the track groups defined, you can create multiple track routes. As you can see that each track route would be represented by a different color, and the moment you click on the route IDs, it will be highlighted automatically on the GIS diagram too. From the electrical system side, I have my high voltage transmission systems feeding by the utilities, the substation structures, and down to my DC substations with rectifiers, and also my DC traction power. On the way side, you can see the model of the energy storage system with the battery management systems, and you can also model your low voltage signaling power systems. Let's take this time to take a look at the energy storage modeling we have in ETAP. You can define the battery management systems by setting the charge and the discharge logics, either with a bus voltage. You define a bus ID, and when the voltage is higher than a certain percentage, that means the system has enough regenerative power that boosted the system voltage, and then the battery can get charged. And vice versa, when the voltage gets lower, then the battery starts discharge the system. Similarly, you can select an operating generation from a certain location by observing the power flow. Certain charge and discharge control parameters can be defined to represent your energy storage system on the way side. Now let's take a look at the trend timetable and how we can define it. Under each route, you may define multiple trend timetables for various what-if analysis. You can define for each different day the trends run under different schedules. There can be unlimited numbers of trends to set the arrival and the departure time. To add more trends to the timetable, you just click on the Add button. Then you can select the number of trends to add, the start time, and the head wait time and the dwell time. The trends would be easily added to the system. We completely understand that within an existing system, especially during rush hours, there would be hundreds of trends running to be taken care of for the timetables. ETAP does support Excel export and import functionalities. So you will be able to convert the data in your timetable database into the Excel format that we provide together with the ETAP software, configure the timetable formats, and just do the import. If any modification is needed or you would like to create a copy of the trend schedule and do modifications on top of it, just use the Excel export and do the modification, then just do the import. This will efficiently reduce the man hours on manipulating with the timetables, interacting with the software. Normally, after the trend timetable is defined, then the next step is to define the rolling stock, where we use the rolling stock libraries. Under the trend rolling stock libraries, you are able to create your own model for AC trends or DC trends, and the models can be under either metric unit or English unit based on your need. Let's take a look at the parameters. You can define the general parameters of the trend nameplate, for example, the auxiliary power, the trend rated voltage, the weight, the rotating mass, the trend length and width, height, and also the electrical parameters of the trend, such as the rated power, the rated voltage current, tractive effort, the maximum speed limit allowed, the maximum tractive effort, the efficiency, and power factor. To do the trend performance calculation, you will need the trend cross-sectional area and the ABC parameters for the Davis equation calculations. In ETAP, you can also define the trend current limitations, which represents that under different voltage levels, your trend current would be limited by the rolling stocks. The trend current limitations can be defined for both the traction and the regenerative braking conditions. These curves are defined based on different European and IEEE standards, where basically you provide the maximum traction current and regen current, the knee points, your auxiliary current, and also your Umax1, Umax2, and Umin2 to define the points and limit the train operating current. ETAP also supports the tractive effort versus speed limitations based on different voltages. As you can see here, for different voltage, each voltage you can define its corresponding tractive effort versus speed curve. This will be used for the tractive effort. Similarly, you can define the maximum braking effort versus speed and also the regenerative effort versus speed. After the rolling stock libraries are defined, you will have a centralized location to store all the data and use it for your future what-if analysis by combining different rolling stocks for each train, and that can be achieved in the eTrax editor again. You can define different train types, which would be used to use different train speed limits and coasting limits for the same route. And then you can select different locomotives and coaches and wagons and so on as different combinations to form train configurations. And different train configurations can be assigned to each train ID under different timetables. Basically, everything is done graphically. You don't have to deal with large text-based database, and this is the easiest way to configure the systems. After the modeling is completed, now we come to the simulation stage. ETAP automatically performs the train performance calculation plus the power flow calculation. Train performance calculation means you utilize all the geographical conditions, the curves, elevation change, and look at the train mechanical conditions, do the performance calculation and turn them to different electrical load profiles at different locations for your electrical system. And then ETAP does a time series unified AC-DC power flow calculation for all the time points that you defined to do the simulation. That means for each load flow calculation, it considers all the substations, AC side, DC side trains simultaneously. And that makes sure your calculation results are the most accurate and precise. As you can see from this diagram that while the simulation is done, you will be able to see the results variation using a time slider on both the one-line electrical diagram and also the geospatial diagram. One feature we want to highlight here regarding the timetable calculation is the concept of free schedule and fixed schedule in ETAP. The most straightforward way to run a traction power flow simulation is to define a timetable with departure and arrival time at different stations and then just follow it. That's what we call fixed schedule. However, under the situations that you need a reference to do a preliminary design of the timetable, or you see deficiencies in an existing timetable, like the supply power quality constrains the train performance, and the timetable needs to be adjusted to accommodate a better voltage profile feeding the trains, then the free schedule feature would be of great help. With free schedule, it considers the first station's departure time from the timetable, and then the speed and the trip time are calculated based on physical and electrical limitations that we saw just now, like the speed limit, the current limitations, the tractive effort limit, impacted by the low voltage, and so on. The free schedule simulation generates one set of timetables by pushing train operations to its limitations and provide a relatively most tight timetable that you can use as a reference to adjust for the future usage. In ETAP, you can also define the events and simulate times and steps. Because this is based on the ETAP platform, So you can benefit from its multidimensional database and then define unlimited what-if simulations, such as different technologies of renewables, of energy storage, different contingency analysis, system configurations, test your new timetable, the new rolling stocks, and so on. The events can be set in the traction study case. In the events, you can define at a specific time what is the event ID and add different types of events to the system that can be open and close of certain protective devices, the voltage variations of the utilities, variations of loads, etc. That would be of great help if you do the contingency analysis. And for the simulations, you can define which days to run and run which route. If you have multiple schedules defined for the one route, you can select which schedule to follow. Of course, as a time-based simulation, you can define the calculation time to be either complete train schedule or a user-defined time range, and also the step to run the calculation. Alerts can be defined as part of the results to let you know the overloading of your lines and cables. Of course, with your transformers and rectifiers with a certain time duration and a time interval, and also your voltage issues on the pantograph with the UMAX 1, UMAX 2, UMIN 1, UMIN 2 concepts from the standards, and also the mean useful voltage for zones and trains that we will explain in a little bit. After all the simulations are done, considering so many parameters to evaluate in a time range, the result dataset can easily go to a huge size. We truly understand your pinpoint and would love to make the results analyzing procedure as simple and efficient as possible. First, to rephrase on the analysis goals, analyze and improve the quality of power delivered to the train sets, perform overloading assessment of wayside equipment and feeders, establish operation restrictions, and carry out energy management to evaluate energy assumptions of different technologies, system configurations, and different operating strategies and policies. ETAP provides synchronized animation results on the GIS and electrical scheme diagrams. Alerts can be generated to pinpoint the problematic time and the location. You can use the plot analyzer to easily compare the results from multiple scenarios results and generate detailed and summary reports. All the plots and reports I'm going to show in a bit, they are customizable because all the results are based on SQLite database. So if you would like to change the parameters we use to generate the calculation indices, or you have specific requirement about how your report and the plot should be using and how you want them to look like, we provide the templates of Python scripts for you to do the customization, and we also provide engineering services to help you customize the scripts to generate the plots and reports, the output that you want. One of the most powerful features in the whole ETAP is the definition of the scenarios and the macros, where you can define unlimited numbers of scenarios to simulate what-if conditions. So here I have already set up 3 scenarios, one for my normal DC train simulation with fixed schedule, the second scenario with free schedule. You can see that I have used a different study case with the free schedule setup. My third scenario is the train BMS simulation, where I consider the battery management system from my wayside energy storage systems, where I use a different configuration or topology to do my simulation. All these different scenarios would be saved together with your ETAP project, And one better approach is to set up a macro in the study wizard where you can have all of them. So assuming in the future, if there's any plan change, any electrical parameter change, that you need to rerun all the studies and regenerate the results to do the analysis, just open the study wizard, click on run, and all the scenarios would be run simultaneously. After that, you just need to do the analysis as the engineer. One powerful feature to analyze the results visually is to use the plot analyzer, where you can select multiple output reports and define the device types, device IDs, and what type of parameter do you like to plot. Here you get to see all the results generated from the power flow calculations for voltages, currents, power flow, energies of different elements. And you can also see that we calculate different parameters, rolling demand, peak demand, and average demand for the cables, transmission lines, transformers, and so on to give you a time-based calculation results. You will also be able to plot the trend performance results, for example, the rolling resistance, the total tractive effort, the trend speed, the locations, and also routes and schedules. So I'm going to show you how to overlay the results of two simulations. Now I selected my DC trend simulation, which used the fixed schedule and also the trend-free schedule. So I'm going to plot the speed and energy, combine them into one plot. So now you can see that the results can be overlaid on top of each other. If you turn on the annotation, you will be able to see at each time if the variation is caused by an event and what is the result for both reports at the same time. This would be a very intuitive way for you to do the analysis. We also provide pretty comprehensive reports for both input and output results. As you can see, there's a list of detailed results that you can create Excel reports for, like the trend performance calculation. In the trend performance calculations, you get all the detailed values for each trend at each time, where they are, and what's the different types of trend resistance and attractive effort correspondingly. ETA provides a few summary reports too, which is very beneficial and efficient for you to have an overview of your system simulation. Let's take the alerts as one example before we look into a few other highlights of the reports. So in the alert report, you will get to see all the violations based on ratings of your elements regarding current, voltages, powers, based on the ratings of your study case alert settings. And because this is a time-based simulation, all of the results would be analyzed based on the time duration to give you a comprehensive picture. As mentioned, we want to make the analysis very efficient, so we try to look for the indices that is able to represent the performance or the operating conditions of your whole system. The zone and the trend mean useful voltage are some great examples. They aim to define the characteristics of fixed installations. The quality index, mean useful, is calculated by simulation of a geographic zone, which takes account of all the trend scheduled to pass through the zone in an appropriate period of time, corresponding to the peak traffic period in the timetable. The voltage values from the simulations are used to study the mean useful for the trend and the mean useful for the zone, are the best representative of your quality of the power supply in the geographic zone to all the trends. And for each trend, we identify the dimensioning trend and quantify the trend performance with one single factor. These results can be seen in the substation summary report and the train summary report. Not only that, you can also find in the substation summary reports that for each transformer, each rectifier, what is the maximum instantaneous current and what is the maximum moving average current over a period. For transformers, of course, not only the current, you also worry about the MVA, operating conditions, the supplied energy, the total regenerative energy of your equipment. As mentioned, you can find the zone mean useful voltage in the substation reports. For each train, you can get the summary of its total traveling time, the mean useful voltage index, and the catenary mean and max voltage during the whole simulation, and also the total consumed and regenerated energy of that train. Another highlight we want to mention is that we understand the sizing of the equipment is not an easy task because the railway equipments feed moving loads. So that means there might be peaks and you need to consider the time duration when you do the sizing. So in E-Trax, we honor the BSEN 50329 standard, where you can select the train service type, for example, the light service, heavy service, extra heavy service, and so on. Based on the standard, ETAP is able to calculate the required size for the train, of course, considering the time duration, the intervals, and the percentage of the MVA base that is defined by the standard. With this feature, you are able to tell whether the design of your equipment is undersized or oversized. So far, we focused mostly on the train performance calculation and the power flow simulations. As one of many solutions in ETAP, you can also benefit from many other solutions, such as perform an unbalanced short circuit study for your system, and then do the overcurrent and distance protection studies using the STAR-Z module. Other standard and popular analysis for railway systems are available too, like the harmonic calculation, substation ground grid design and evaluation, cable thermal analysis, arc flash analysis, and so on. Go to ETAP website to find more applications that suit your needs. By connecting your electrical design model with real-time analytics, you get additional level of reliability, operation safety, and cost savings. The intelligent monitoring system provides intuitive, intelligent, and integrated real-time monitoring via a state-of-the-art interface. You can also use the eSCADA systems to evaluate the cause and effect investigations, system operations, alternative actions, and what-if scenarios. Predict and trend system loading based on algorithms that adaptively correlate input variables like weather conditions. Predict the system behavior in response to operator actions and events using real-time and archived data. Web-based applications and views to visualize, simulate, and manage. Detailed energy consumption and cost analysis based on energy tariffs and power market exchange information. You can also go by intelligent analysis processes to manage the monitored data for substation level and central system evaluation. The turnkey SCADA solution with open architecture and native communications, the interface for monitoring, control, and automation for substations would be great choices too. On top of that, you can also analyze the disturbances, islanding conditions, the stability limits, and detect abnormalities in the system through intelligent electronic devices. To summarize today's webinar, we went through a solution overview for E-Trax, which is a great solution for the railway design, analysis, and operation. We went over the showcases from modeling to simulation to help you have an understanding of the seamless procedure using the product. eTrax is the analysis tool that you need to get the results most efficiently. And then we had a brief introduction of the real-time traction power management system. Thank you for your time. For any questions, please feel free to reach out. Have a nice day. Bye-bye.